Hey, good morning, everybody. Um, I want to start with two remarks about last week. First of all, in some problem solving one, I noticed that the grader incorrectly canceled out like other classifications, like nominal or ordinal. They all were correct. So if you have some points taken uh, for the problem one, just let me know. Um, the second thing, my mistake. um, it looks like one student at least understood the notion of Iverson brackets because only one student contacted me and pointed out um, to a mistake in my definition of accuracy. So in this definition, I should use equal to if I want to cancel the correct guesses. Then this statement will be true if there y equals y. Otherwise, if I'm using this not equal sign, I will count the number of errors. Instead of accuracy, it will calculate one minus accuracy. So we should correct this to equality. Otherwise, instead of 90%, it would be 10%, just error. Okay, so the plan for today is to talk about k-nearest neighbors for regression. And by regression, we mean prediction of continuous data. And exploratory data analysis, there will be a notebook that you will fill in by the end of this day. So, assume we have some continuous data. I don't know what they can represent, some points, and we want to evaluate this function in some intermediate points. So how can we predict the value of our feature in intermediate points using neighbors, for example, two neighbors? What would be the reasonable prediction? So the topic is k nearest neighbors for regression. So our training points are these ones, x, for example, 1, y1, then x2, oops, it's I, then x2, y2. So we have these pairs. So y represents the height. How to predict the value at this point? Let's call it x star. What would be the reasonable prediction using two neighbors? Yes.
Maybe take the average of the
average. So this is the first that comes into mind. If we have if we take into account 3 points, then we will take the average of 3 points. And if we take into account all the points, we would predict just by the mean value of all these points. So in case of 2 neighbors, we can predict this point. Y star as the average of these 2 neighboring points y1 and y2 by 2. And in general, if we take the k-nearest neighbors, we would use the formula for y star 1 over k, where k is the number of neighbors, and sum for I from 1 to k, y with indices. You remember we sort our points, and I use double index. So let's call it ik, and then it will be index k. So just the average. If we want to, so let's look at the example. So this plot represents the following violin recording. So this is an algorithm that detects the pitch, but you can see that it's noisy. Also the violinists use vibrato. So if I want to predict the pitch from the melody, maybe we want to get just one letter, like do you remember what is the frequency for A?
440.
440. So you can guess where was A here, maybe.
From that third one.
Maybe this one. Yep. Then it would be C, C, B, A, G. So maybe we want just to predict one number or one frequency or one letter A. So we can apply these k-nearest neighbors. And here is the result if we apply, to be honest, I don't remember how many neighbors, 15 neighbors, k equals 15, 15 neighbors. Then our data will be more smooth. But still, we have some points that we call outliers. We'll talk today about how to detect outliers. And also some outliers that I mean, this was just the silence, and there was some noise, like ambient noise, that provided this outliers here. So yeah, when we take these k-nearest neighbors applied, then it will smooth our detection. But next class we will talk about how to get better prediction for this, to get just exact classes for nodes A, B, C. Okay, do you have any questions about k-nearest neighbors for prediction of the continuous data? If not, let's talk about how to measure the quality of our prediction. We will talk about 7 metrics for quality, but for today, I will just mention 3. I can say most common because others are also common, but the 3 metrics that we will use mostly: mean squared error. So for mean squared error, we will check the difference, L2 difference, L2 squared between points y and their predictions, y hat. And this means that we take the 1 over n, without 1 over n. Oh, actually it's mean, then we should take 1 over n. Okay. 1 over n. And here we will have sum over all points. And just square difference. Oh, actually, here, I'm sorry, I should use without index I, just the vector of all predictions y and all targets y. Because this metric is actually the sum of all components. The problem with this metric is that even though it shows the closeness of the points, but it changes the units. For example, if we predict the price, then we will get squared dollars. How to get the normal units? To take squares. So the other metric is called RMSE, root mean squared error. So RMSE is just the square root of MSE. The next metric that also returns correct units is called mean average error, MAE. So it's the same formula, but instead of square, we take absolute difference. And the most common is in statistics metric is called R squared. So the last metric that I want to mention for today, R squared is defined as 1 minus prediction. And so in numerator, we have the sum of squared errors. And in denominator, we subtract the mean value. So it means if we predict everything by average, like the most the simplest prediction, if every y hat I is just the average, what we will get as the result of this fraction, if every y hat is equal to y bar. it will be 1. And the R squared metric will be 0. If our prediction is 100% correct, if our y hat equals y, then this fraction will be 0, and our it's called coefficient of determination R squared will be 1. So the best value will be 1. But the worst value can be negative. if we predict that by something worse than average, we can get actually this fraction greater than 1. But the 1 is the best. So R squared is no greater than 1. And, okay, now let's go to the practice. Let's open the notebook. Notebook. Which is called exploratory data analysis. So upload, import our libraries. The new library for you maybe today is Seaborn library. We will use this to plot nice histograms, bar plots, violin plots, and so on. And upload this data. Okay, last time I mentioned how you can use this Linux comments. We don't need this for now. Read data and visualize our first 5 records. So today we will work with Titanic dataset with information about passengers and let's think about, so we have passenger ID, survived or not, yes, passenger class name, sex, age, siblings, number of siblings like brothers, sisters, parch, ticket, fare, paid, and the port of embarking. So what do you think, which column will be our target? What do we want to predict for a passenger? Yes, just correct. So we will predict, so this will be our target. So our problem will be a classification or regression problem. So we talked about k-nearest neighbors for classification and k-nearest neighbors for regression. Yeah, classification. So when we want to just classify 0, 1, survive, not survive, then it's called classification. If we want to predict some, for example, age, like real numbers, then it's called regression task. The first step to assess your data, again, we talked about how to read column names. Or how to access by name using lock. So the first step is to look at the data types and for numerical columns features, to look at the statistics. For example, or wait a second. Sorry, here I'm just showing that you can reset the index, like you can make name as index, and then if you want to. Okay, let's look at the information. So first we look at the number of data points. We have about 900 passengers, information about 100 passengers. Then we can look at the statistics, and for example, in this case, we don't have this problem, but maybe you would see negative numbers for age, then it would be a red flag that there is something wrong with data or outliers or missing values. So you can just observe some statistics to, like, for example, the range of your data, mean, max, or average, just to assess the data. Then you can look at the number of not numerical data. Data in 4 will print this information. All data types objects are not numerical, so these are columns that we should take care of. Also, you can see the counts, and if the number is smaller than in other columns, it means that there are missing values, because it counts non-null, which is not a, not nonce. Also, it means that we should somehow work with these columns. Okay, so this is the task of the exploratory data analysis, to explore the data, to clean the data, and prepare them for our models, for algorithms. Oh, here is the plot. I just plotted the information about missing values. So you can see that there are a lot of missing values on age and kNN. Cool. But also some in the port embarked. Okay, so the exploratory data analysis we will perform for every column. So we will look at every feature. First of all, let's think about if passenger ID is informative feature. What is it? Do we need passenger ID? No, we don't, because it's just the index. Survives is our target. So let's look at our target first. And there is a method which is called value count. Value count just counts the all unique values in your column. Why do we want to look at this drop and a false? So if you don't use drop and a false, you won't see if there are missing values. If there, we will see later if we have missing values, we will see also none and count of nones. So the purpose of the count of the target is to understand if our data is balanced or unbalanced. Because if we have, for example, 90% of one class, and we predict everything by this class, we will get accuracy 90%. But it doesn't mean that our algorithm is good enough, because we just predict everything by the majority of the class. So the accuracy is a good metric only if data is balanced. Here it's quite balanced, 500, 300. And we can plot, bar plot, just to visualize the number of passengers in both classes. Okay, this is how we plot in just with pandas. Pandas has this bar plot function. And this is how we plot with Seaborn. So it looks usually nicer, and normalize means that we want to get the probabilities that these proportions sum up to 1. If we don't use normalize, then we would get counts. Well, and now we begin so-called one-factor analysis. One-factor analysis means that we will look at one feature at a time. So next feature is passenger class, then name, sex. Okay, let's see what's the next feature. Passenger class. We begin, because passenger class is a discrete variable, we again look at the counts. So we have three possible values for class, the first class, second, third. And now we can plot the bar plot. Bar plot. But if we want to understand if this feature was important for survived or not survived our passenger, we should plot the distribution of classes only for survived passengers. So we can plot, we can group by passenger class and plot only the total number of survived passengers. And how to, so these are the counts for only survived passengers for class 1, class 2, and class 3. So how to answer the question if this feature is important or not? Just looking at this distribution of bar plot. So what? Let's think about the situation when all the proportions are the same. What do you think? In that case, the class would be informative feature or not? Yes, you can just speak
What
about
about not? Because if they're all exactly the same, that doesn't mean it's had an impact on the other
Yes.
thing.
So how to answer the question just looking at these plots, if this feature important or not? If they're not,
It's okay. There's usually a little correspondence, but it's not super strong.
if they're not like equal, then we assume that this feature has some influence on on our target.
So I was thinking that maybe if you added more people, like added more.
Yeah, then more people will
Yeah.
die. In that
Yeah,
way.
I don't
Yeah,
think
more
really-
people.
There's not, I mean, there does seem like a weak correlation, but I just don't think there's enough people to really state whether or not there's any kind of correlation.
Well, if the number of people before than 30, it's okay. For to evaluate the correlation. So okay, so also you can plot both classes like so the green color represents the distribution of the survived people depending on the class. And actually, you can see that there are more survived people in the first class. So just an interesting observation. And the number of not survived people. Okay, the next column is sex. And again, it's categorical, so I will visualize the what's called the unique data. And here's the case when we have missing values. It's not nonce, it has just the string title unknown, but still it's missing value. So let's look at these 5 records. Oh, here, first I visualize the data. This is bar plot, and then I visualize the I look at this bar plot only for survived people to answer the question if this feature important or not. Because if it's not important, we'll just drop this column. If it's important, we should take care of missing about missing bits. So, is it important? The sex for the survive. How to pronounce it? Say the survivalness.
Correct. Yeah.
Yes. So yeah, it's important. So in this case, we should take care of. I just provided different examples of bar plots. What is this plot? This plot represents the percentage in each group. So, like, we have 5 passengers, and it looks like this fraction, which is well, this is another plot that just shows the proportion of survived passengers in each individual class. So, like 20% of male class survived, and so on. So it's another plot. So let's take a look at these missing values. We can use data and use this condition data.sex, or we could use the brackets equals unknown. It will print only the records with unknown sex. So what do you think how to handle these 5 records with colon sex unknown? Yes.
You could make inference off of their names.
Yes, so if we have just and a few data points, and maybe we can figure out from the names, like Mr. Yes. Yes.
Yeah, right.
Yes, so if we have just few data points, the good idea just to remove these records. But we should be mindful, because if we remove 5 records for one column, 5 records for another column, 5 records for the next column, maybe we will remove half of the data at the end. So let's, I will show you two things. First thing, we can just looking at the indices. For example, the first is Mr. This passenger has index 5. The next Mr. has index 13. I can manually assign the feature name to the records with indices 5 and 13, for example. And then the number of unknowns will decrease. But it was a good idea just to remove this data, and we can drop by index where index where we take index only for records with sets feature equals unknown. And in place equals true, it will apply to our data set. And after that, when we plot the distribution, we will have only 2 classes. So, okay, next thing. The names of these classes are not textual, not numerical. We should convert this into numbers. Last time we applied just map function to our data point and mapped male into 0 and no, male into 1 and else to 0. But I want to show you the automatic method in pandas, which is called one-hot encoder. So first we should import this one-hot encoder class from scikit-learn. And next we create the instance of this class. And we always use drop first. I will show later what does it mean. So then we apply a method fit on our column sets. And we can look at the categories, and then we can apply transform. So I used fit, so I can use just transform. Transform and because it returns sparse matrix, we use also toArray, because if I'm not using toArray, I will get just the what? Wait a second. Oh, maybe I should use just data. No, 1 second. Oh, I did I did something. I changed my column, so I will need to upload my data again. Let's see if I changed my column data. Yeah, I changed my column data into sparse matrix. So I will need to read my data again. Okay. I just canceled my feature. Sucks. Okay, read. Run everything again until one hot encoder. I didn't notice that I actually rewrote my data, like data.sex equal, and so okay. So we create one hot encoder, feed it on the column 6, and then I can show you the result. One hot encoder transform of data 6. So if I'm not using to array, it would return just the sparse matrix object. To array will return just the normal NumPy array. And I'm not sure if it looks I can't apply just to one column. Yeah, I should apply to the data frame. So if I'm using just data of sets, it returns so-called series data type, just one-dimensional array. If I'm using data of the list of columns, it returns data frame, two-dimensional array. So it looks like this works only for data frame. And if I'm not using drop first, I will get two columns. So I think you can figure out what does this drop first do. It just drops the first column. So it maps it's important because we will use one hot encoder all the time in this course. So if we have two categories, for example, M and F, and we have a column M, F, F, for example, then one hot encoder will return two columns. One column will assign 1 if there was M, and the second column will assign 1 if there was F. So this is the output of one hot encoder. Instead of one column, so if you would have 3 classes, it would create 3 columns. And you would see ones only on the place of the class corresponding to this column. But if you have just one column, you can guess the result of the second column because they sum up to 1. And when we will work later with linear regression, we don't want to have dependent columns because in that case we wouldn't be able to inverse the matrix. So to avoid what is called multi-collinearity, we always drop one column, because if we have two columns, they linearly dependent. Just one is column equals one minus the second column. So that's why in this processing, we use drop first. Of course, you could drop the last, but drop first is just built-in method. We feed the data, we transform the data, and finally we reassign the value of this column and the result looks as follows. So in place of column sex, instead of male, female, we have ones or zeros. Okay, so and also oh, I skipped one line, and now we go to the next feature age. If I print all missing values for age, then you will see there are a lot of missing values. 100, about 200 records. Do we want to remove these lines with missing value for age? Maybe not, because in this case we will remove we had 900 records, so we will remove about 1/5 of our data. So how to work with missing values for age? If we don't want to remove, we don't have any clues. Well, maybe we can look at if they had parents and somehow get, but it's very time consuming. If you work with data, you should know about how to work with missing values for numerical data. We can estimate the average of all passengers and assign the age as just mean value over all passengers. But in practice, so there is this, we can do this manually. So let's see, I plot here a histogram. Aha, and you remember last time we talked about the window function that dropped down to get the weights for k-nearest neighbors. So, and there was parameter h, which corresponds to the width of this kernel. So the histogram, I hope you know how histogram is plotted. You just split the range into bins and count how many people with age in this bin and plot this. But there's also KDE, which is kernel density estimation function that can plot the continuous distribution of your data. And this KDE actually has also parameter h. This is the default parameter h1, but if I'm using for smaller h 0.5, then you can see that this kernel density estimation will be more uneven because it will take less neighbors into consideration. I just want to show you another application of this parameter h in the kernel. If h is large, the curve will be more smooth. If h is small, the curve will be will follow your data more. So if we look at this plot, we can figure out the most common age of the passengers. So it's in this range between 20 and 40. And what do you think is better to assign, the mean or median? So I think I calculate here mean and median. So median is 28, the mean is about 30. So which what's called statistics is more representative for data, like for salaries? Yeah.
I think like the median works better because like there's no like very big outliers. So we can use the median for this one.
We can use, and this is default settings in the next function that we will use, imputer. But in general, actually, you remember the example with salaries, like few people have maybe billions of dollars salary, and this will shift your mean to the higher salaries range. But if you use median, you remember in median, we sort our data in increasing order and take the value with index n over 2. So if we look at the median of the salaries, we will get the salary, most common salary. If we look at the mean, we will look at the average salary, but again, some people can have zero, some people have a huge amount, but in average, they will get some reasonable amount of income. So it's a good idea to use mean in data science. But okay. There, of course, we could assign the mean age just manually, but there is a built-in function which is called imputer. There are different strategies, mean, median, and so on. By default, it's median. Oh, it's mean by default. Sorry. So I import simple imputer, and we could use separately fit transform, or we can use in one line fit transform on our data. It will look at our data, calculate the average over nonce, and then we will assign this value to our column H. If I plot again our distribution, it will look like this. We will get a peak for around mean, but it's because we just inserted 200 means in our data. But still, the general outlook of our outline of our density looks as good, correct as previous. But now we don't have missing values in our column H. Now there are three columns for you guys. So embarked, what I want from you to do just to plot to just copy paste the code for our column sex, just to count how many unique values for each class, to plot the bar plot for survived, just to assess if this feature is important. And if there are missing values, just drop these lines or so. I will go with you, but you can work yours on your own. So there are three features, or actually 4 features that we want to analyze: embarked, siblings, parch, cabin. So the goal of this pre-processing is to get all the features as numbers. So embarked. Actually, you just start typing and it provides the correct code. So we have 2 missing values. 2 is a small number. We can just drop these records. Was that the remove? Oh, I don't remember what was this. Or it was drop, maybe. So I think this code will work. It will drop the lines by missing values in a bark. Because you remember I used a little bit different syntax, drop by index, and then I calculated the index for missing values. But I believe AI assistant knows better better pandas than me. So let's see if we do that and look at the counts again. Yeah, it just dropped these two lines. But before dropping, actually, we had to plot the importance, and again, it understands what I want. Yeah. So it looks like the port where passenger actually embarked is important. I don't know why. Okay, so you should do just the same 3 lines of code for all other features. So, well, it's good that in the next feature we don't have missing values. So, arch. So in Parch we also don't have missing values. That's good. Feature is important. And the last feature, cabin. So with cabin, there is a problem. There are more than there is about 60% of missing data. And again, it's really hard to reconstruct the cabin name from 100 years ago event. So what would be the best solution? Yes. Yes, we will just we won't take into consideration this column at all. So let's see if I'm removing this column later, or we should remove it now. Oh, actually, I just will remove it later, so you can just leave the counts for cabin. Okay. So you remember in Embarked we had non-numerical labels C, Q, and S. So we should apply one hot encoder to this label, to this column. So I create one hot encoder. If you have non-numerical categorical data as targets, then you should use label encoder. So label encoder is used for Y's. One hot encoder is used for X's. There's also ordinal encoder. If you have like ordinal data, it will assign numbers 1 to 3 for these classes. But we will use one hot encoder because we don't have preferences for ports. And again, so I had this object initialized one hot encoder. And when I apply to Embarked, it will return 2 columns because the first is dropped. And these are the class names. And I create a new column with only 2 class names Q and S because the first was dropped. And here's how my data set looks like now. So we have 2 more columns with names S and Q. And now we are ready to get the final data table. So we will take this column survived as target, passenger class, sex, age, siblings, part, fare, embarked, but embarked like as 2 last columns as our features. And here's the code. I separate targets Y and X. In X, I take only these columns. Survive passenger ID. Wait a second. I don't need passenger ID. Oh, it's drop. It's drop. Okay, I dropped these columns. Survive passenger ID, name, ticket, cabin, and embarked. And ticket. I dropped ticket because ticket is text data, and we will work with text data in week 4. So for now, we'll just skip it. And then scikit-learn has this function train test split. It will split by default, it's 30% our data. The only thing that, and after that, we can print our train data, and this will look like a normal numerical table. There will, did you have a question?
Yeah, I was gonna ask about what the test size just.
So
Size.
for now, use default, and for homework, use default one. Just don't indicate it. And the only thing about this train test split that I kind of skip this. When you impute your age, you should take the mean age only over the train set, because you remember test set, we assume that we didn't see this data. So when so next time we will fix that. We will calculate mean age only over. So first we will split data into train and test, and then we will actually impute and work with missing values and so on. Because we assume that we don't have any, we don't see test data, so we don't know age in test data. But for now, I just to simplify that, we'll skip. And now, when we prepare this nice table, we can use any model from scikit-learn. It doesn't matter if you don't know how this model works. You just import this model. Well, but at least we know how k-nearest neighbors works, and apply this model to your data. So here I create the k-nearest neighbors with 3 neighbors and use fit on x train, y train. But you could import logistic regression, you could import support vector machine, you could import any model, and now it will work on your prepared data. Fit and then predict. I predict on the test, and then we can calculate accuracy manually, like this. Just compare if the prediction coincides with the true value of test. But in every model, there is a built-in function which is called score. Well, it understands what I want to write, score. And the score for classification is the same as accuracy. You could also import, for regression, for your homework, score is by default R². Don't use accuracy for the this week homework. I mean, this homework too. And we have 1 minute left, I think. I just want to mention two-factor analysis. So for two-factor analysis, we can plot 2 features on the same plot. So here I plot so-called box plot or box with whiskers. And in this plot, you can see these plots for what is that? Age and passenger class. So you can see actually what was the average age. In this case, this line it stands for mean. For not sorry, not for mean. For the second quantile, and second quantile is median. So what was the median for not survived people? What was in the first class? So this plot represents kind of two features and dependency on the target. So these lines stand for first quartile and third quartile. So in other words, when we sort our data and we take the index with n/4, it's the first quartile, or with index 3/4 of n, it's the third quartile. And this risk is, there is a formula for viscous the formula, it's different for different packages, but for scikit-learn, it's the difference, it's called interquartile difference times 1.5. And all the points that fall outside, we can call outliers. There's no definition of outlier because it can be just a rare event. For example, the flight, the passenger flight crashed. It's very rare event, but maybe it's the most important actually data for prediction of the of the safety, if you want to predict the safety so of the flight. So it's hard to say what is the outlier, what is the wrong input data, what is the rare event, but as a rule of thumb, we can use this like viscous for these boxes. And if you plot, if I plot the this plot for violin without outliers, you can see the plot looks nicer than with outliers. There's no this first line here. And okay, just the last plot for today. If you uncomment this line, you will plot so-called violin plots, which also two-factor analysis, but it plots the distribution, like you remember the kernel density estimation instead of box plot for survived and not survived people in class 3 and so on. Okay, so that's it for today. Yeah, submit your notebooks by the end of the day. And next time we will talk about pipelines, how to do this all automatically in one line.